Welcome to the Discrete Universe podcast. Today, we're diving deep into something called quantum geometry dynamics, QGD. It's an axiomatic approach to physics. And our big question today is really, how do QGD's core ideas explain some of these observations that, well, seem to challenge the standard cosmological model, LIGO-Virgo? This is aimed at you, our physics-savvy listeners, so we'll be unpacking these challenges using QGD's unique perspective. Let's maybe start with the basics. QGD is built on axioms, right?
Yep.
And the first big one is about space itself.
Precisely. QGD starts from the idea that space isn't, smooth and continuous. It's fundamentally discrete. It's made of these static units. They're called preons. And the key thing is they aren't in space. They literally are space.
Okay, so like pixels on a screen, they make up the screen itself.
That's a good analogy, yeah. They're the fundamental elements. Then you have matter. QGD says matter is made of conserved kinetic things called preons plus.
Right, preons plus. So if those are the building blocks, how do we get to, well, the stuff we actually see? Stars, galaxies.
Well, that's one of the really interesting parts. In QGD, all the visible matter we see originates from these free preons plus. But here's the twist. The free preons plus themselves are dark.
They're dark. So how does the light turn on, so to speak?
It's through a conversion process. These kinetic preons plus can convert into more massive particles. That conversion is really central to how QGD explains how the visible universe emerged.
Okay, that's a very different foundation. And it ties into some recent cosmological puzzles, doesn't it? Like these super early massive galaxies JWST is seeing.
Exactly. JWST found these ultramassive galaxies way back in the first billion years. And the weird part is how efficiently they seem to have turned gas into stars.
How efficient are we talking?
Like maybe 50% baryon conversion efficiency. That's 2 or 3 times higher than we see in galaxies later on. ΛCDM, the standard model, really struggles to explain that kind of rapid, efficient star formation so early.
Right. Standard models expect things to build up more gradually, more mergers, less efficiency early on.
Yeah, it suggests maybe the initial conditions weren't quite what we thought, or the processes were different within that standard framework.
So how does QGD, with its preons and discrete space, approach this? Why would galaxies form so fast and efficiently?
QGD suggests a couple of things. First, in the very early universe, you'd expect some regions to be incredibly dense with these fundamental preons plus just, more raw material locally. And second, maybe the conditions back then were just right for a much more efficient conversion of those preons plus into visible matter, into stars.
Okay, so higher density, the fundamental building blocks, and maybe a better conversion rate. But what about that specific baryon conversion efficiency number? Is it really baryons being converted?
Well, that's where QGD offers a different interpretation. It suggests that what we're calculating as high baryon conversion efficiency might be, let's say, an artifact.
An artifact.
Yeah, an artifact of analyzing a process fundamentally driven by preon plus density and conversion through the lens of a model based on baryonic mass inside dark matter halos. QGD says the underlying driver is different. It's the preons.
I see. So the calculation method, based on standard assumptions, gives a number that looks weird from the standard perspective, but makes sense if the underlying physics involves preons.
That's the idea. It reframes the observation.
Okay, let's shift gears a bit, move forward in cosmic time. There's this data from DSI, the Dark Energy Spectroscopic Instrument. It seems to hint that dark energy might not be constant.
Right. The influence might be weakening over time. That pushes towards models where dark energy evolves rather than being Einstein's cosmological constant, which is, well, constant.
That obviously poses a challenge to the C in TDM, the cosmological constant.
It definitely does. It makes you question if dark energy is really just a property of space itself or something more dynamic.
So how does QGD handle cosmic acceleration? Does it even need dark energy in the same way?
Yeah.
And can it accommodate these hints?
QGD has a built-in explanation for acceleration. It proposes that gravity fundamentally changes character at very large scale.
Changes character.
Yeah. Beyond a certain distance threshold, which QGD calls day, gravity stops being purely attractive and actually becomes repulsive. And this repulsion gets stronger with distance.
Wow. Okay, so no need for a separate dark energy field.
Not in the same way. This large-scale repulsive gravity is just part of how gravity works in QGD. It naturally explains the accelerated expansion we observe.
And the hints that the effect might be changing.
That could potentially fit too. If the way this repulsive force scales with distance leads to a changing overall effect on the expansion rate over cosmic history, then you'd see something that looks like evolving dark energy, but it would just be a feature of QGD's gravity itself.
Interesting. Okay, another tension point. The clumpiness of matter, the S8 parameter. Late universe measurements seem to show less clumping than the early universe data from Planck suggests.
Yes, the S8 tension. It's a persistent headache. Weak lensing surveys of the nearby universe give a lower S8 than what you'd expect based on the CMB fluctuations from the early universe, assuming CDM is correct.
It suggests something's off in how we model structure growth over billions of years.
Pretty much. It implies maybe ACDM is missing something about how matter clusters.
How does QGD address this, especially given its different take on matter itself?
Well, this ties back to QGD's view of dark matter. Remember, QGD doesn't need some new exotic dark matter particle.
Right, dark matter is just the free preons plus that it haven't converted yet.
Exactly. And QGD predicts a specific relationship between where visible matter is and where this dark preonic matter is. Regions with lots of stars and gas would actually have proportionally less dark matter nearby. Dark matter density would be higher primarily where you already have visible matter.
That's completely different from the standard picture of huge dominant dark matter halos engulfing galaxies.
Totally different. And it leads to different predictions. QGD expects galaxy rotation curves to stay flat further out than standard models might predict. And crucially, it forbids these cuspy halos, sharp density spikes of dark matter at galaxy centers that standard simulations often produce, but observations haven't really confirmed.
Okay, so different matter distribution, different dynamics. How does that help with S8?
If dark matter behaves and distributes differently, then the whole process of large-scale structure formation, how clumps grow over cosmic time, will be different. QGD's framework naturally leads to a different prediction for the evolution of clumpiness, which could potentially resolve the S8 tension without having to, invent new physics within CDM. It comes out of QGD's core axioms.
It avoids adding epicycles, perhaps.
You could say that. It's a consequence of the fundamental theory, not an add-on.
Let's go back to JWST in the early universe again.
Yeah.
It wasn't just the mass of those early galaxies, but their shape, right? These surprisingly smooth, settled disks appearing early on.
Yes, featureless disks. They look quite mature, more ordered than you'd expect from the chaotic, merger-heavy picture, often painted by ACDM simulations for that era.
So CDM expects more train wrecks, basically.
Kind of, yeah. More irregular, clumpy structures forming through collisions. Seeing settled disks so early is another puzzle.
How might QGD's preon-based formation process explain these early, smooth shapes?
Well, because QGD starts with a different fundamental picture of how matter itself comes together coalescing from this preonic field under QGD's specific gravitational rules, the whole pathway of galaxy formation could be different. It might allow for these ordered structures to form more rapidly and perhaps more smoothly than through the purely hierarchical merging process in ACDM.
A different path to structure. Okay, now closer to home. Andromeda, our big neighbor galaxy. Its satellite galaxies are weirdly arranged.
Ah, yes. The satellite problem, specifically for M31, instead of being scattered randomly, a lot of Andromeda's dwarf satellites lie in this vast, thin plane, the vast polar structure. And it seems kind of pointed towards us, the Milky Way.
Which is odd, because ACDM generally predicts a more isotropic or random distribution of satellites. Simulations struggle with this, right?
They do. Reproducing such a strong, coherent alignment across almost the entire satellite population, and especially its orientation relative to the Milky Way, is very difficult in standard cosmological simulations like, say, TNG-50. They just don't see that kind of large-scale asymmetry pop up very often, especially not pointing towards the simulated Milky Way.
So could QGD, with its different gravity and matter formation, offer a way out here too?
It's possible. Again, because the fundamental dynamics of how structures form and interact are different in QGD, simulations based on its principles might naturally produce these kinds of asymmetric satellite configurations that are rare or unexplained in ACDM. It offers a different dynamical playground, essentially.
Okay, let's tackle something really fundamental now. Gravitational waves, or what LIGO and Virgo are detecting, especially GW170820, the neutron star merger with light seen alongside the signal. QGD has a very different view here, doesn't it? Because of discrete space.
A very different view, yes. Since space is discrete in QGD, made of these preons minus, the whole concept of space-time being a smooth fabric that can ripple just doesn't apply. So QGD fundamentally precludes gravitational waves as described by general relativity.
So what are the LIGO-Virgo signals then? according to QGD?
QGD interprets them as preonic waves. Think of the underlying preonic field, the fabric of space itself. When massive objects like black holes or neutron stars move violently, they cause disturbances like polarization changes or oscillations in this fundamental preonic field. These disturbances propagate outwards.
Not ripples in space-time, but ripples of the discrete space units themselves.
Sort of, yes. It's a different kind of wave phenomenon inherent to the discrete structure.
And GW170817, with the light arriving almost simultaneously, how does that fit? GR predicts gravitational waves travel at light speed, mostly.
QGD also predicts these preonic waves travel at the speed of light. Why? Because the speed of light, c, is fundamentally the intrinsic speed of the kinetic preons plus the matter constituents. So the near simultaneous arrival of the LIGO signal and the gamma rays and other light from GW1787817 is actually seen as support for the preonic wave interpretation in QGD. Both the wave in the preonic field and the light travel at the same fundamental speed c.
But are the detectors sensitive to these preonic waves? And could the signals be something else?
QGD suggests that yes, the detectors could be sensitive to these kinds of fundamental field disturbances, but it also raises another possibility, that the detectors, being incredibly sensitive, might also be picking up subtle electromagnetic effects. QGD posits that under extreme conditions, like merging binaries, interactions involving these preons plus could generate specific kinds of electromagnetic radiation, maybe involving polarized preons or something termed dark photons, which might mimic the expected signal profiles of gravitational waves.
Dark photons arising from preon interactions.
That's part of the theoretical framework. The idea is that these electromagnetic signals originating from processes involving the fundamental dark preons could be misinterpreted as gravitational waves within the standard GR framework, especially given the detector's sensitivity.
That's a radical reinterpretation. It really hinges on the fundamental nature of space and time in QGD. Can we recap that quickly?
Sure. So space is discrete. The smooth Euclidean space we're used to is just an approximation that emerges at larger scales. And time. Time isn't fundamental in QGD, it's relational.
Relational. So time dilation in special relativity isn't time itself stretching.
No. QGD explains it as physical mechanisms, clocks, biological processes, anything physical literally slowing down in moving systems. This happens because all fundamental interactions are mediated by preons plus moving at a constant intrinsic speed c. If a system is moving, some of that intrinsic motion budget is used for the bulk movement, leaving less for internal processes, making them run slower relative to a stationary observer. Time itself doesn't change.
Okay, and the implications of QGD's gravity model. We touched on the repulsive part.
Right, so gravity has both attractive and repulsive aspects, switching over at that large distance scale day. The repulsion explains dark energy. The collective gravitational effect of all the unconverted free preons plus throughout the universe potentially explains what we call dark matter effects.
So dark energy and dark matter are both potentially just consequences of QGD's view of gravity and the preonic constituents of the universe.
That's the claim. And maybe the most mind-bending implication is that QGD predicts gravitational effects are instantaneous.
Instantaneous. That throws a wrench in conventional ideas about causality and locality.
It certainly does. It implies a form of non-local connection mediated by the preonic field, which is a profound departure from standard physics.
Wow. Okay, we've really only scratched the surface here, haven't we? We've seen how QGD attempts to tackle major cosmological puzzles, from those super early galaxies and the dark energy mystery to the weird satellite setup around Andromeda and even reinterpreting LIGO's signals.
It really offers a fundamentally different picture, all stemming from those core axioms about discrete space and these preonic particles.
The idea that gravity could switch from pull to push at vast distances, or that dark matter and dark energy aren't new things, but just how the fundamental preons and gravity behave.
Yeah.
That's genuinely thought-provoking.
It is, and what's compelling from a theoretical standpoint is the potential unification explaining multiple anomalies from a single, consistent axiomatic foundation, rather than adding new ingredients to the standard model for each problem.
This whole deep dive really highlights how powerful these alternative axiomatic approaches can be in, well, shaking things up and forcing us to question established ideas. It opens up so many questions.
Absolutely. Like, what does a truly discrete space-time mean for quantum field theory, for our most basic understanding of interactions?
And crucially, how could we test this? How could we design experiments or observations that could definitively tell the difference between QGD's predictions and those of FDM or general relativity?
Those are the million-dollar questions, aren't they? It requires working out more detailed predictions from QGD and figuring out where they most significantly diverge from the standard models in observable ways.
Definitely fascinating territory. These are the kinds of questions that keep physics moving forward. We really encourage you, our listeners, to maybe dig into the sources linked with this discussion and continue exploring these ideas. It's quite a different way of looking at the cosmos.